Okay, good evening, everyone, and welcome to the October 7th edition of the Royal Astronomical Society, Ottawa Centre's monthly meeting. So we've got a fairly full program for you tonight, but before we get into that, I'd like to say welcome to everyone. Thank you for coming down. We always enjoy having some new people here, as well as seeing familiar older faces and more familiar younger faces as well. But just as usual, let me ask, are there any people who are here for the first time tonight? This is the perennial joke where everyone puts their hands up, but fair enough. I'm going to assume that there's at least one out there who hasn't been to the meeting before. So, okay, I've got a couple I actually have faith are new to the meetings. Welcome. I'd like to say right off the bat that everyone is welcome at these meetings. You do not have to be a member of the society to attend. You can attend for the rest of your life without becoming a member if you like. However, we'd like to encourage you to become a member of the society if you do find that this topic is interesting to you, if you enjoy coming out to the meetings, and other benefits that you can get from being a member of the society. So let me just grab my notes here, because I'm absent-minded, to say the least. A little bit of light, there we go. A little bit of glasses so I can see, and we'll jump in. So first of all, let's talk a little bit about the benefits of membership, just so everybody gets it. In Ottawa, just the Ottawa Centre itself offers a number of benefits to members. Long list. I don't think I'll go over all of it. However, I'll mention a couple of things that I think everyone benefits from. First of all, there's a monthly newsletter, very high quality, that's produced, has a lot of articles on topics pertinent to various areas of astronomy. It also has minutes of these meetings each time. So if you can't attend the meetings themselves, you're able to read through and see what happened. As well as that, it lets you keep a permanent record if you find some of the talks interesting. And there are some very good talks. Access to the Fred Lossing Observatory. The Society has a observatory out near Almont, I guess I would say. Has a nice telescope. It's got a warm room for you to get warmed up again if you're observing late at night. Members can get access to that observatory and are able to use the telescope after they've gotten a bit of training. So a very fine instrument to use for your personal observing. Access to books, access to telescopes for very modest prices. So if you're interested in trying out different types of telescopes, you can borrow them from the club's loan library and use them. Many other events. So, without belaboring the point, it's worth looking at. Memberships are done through the national web site. They're not done here. We don't collect any fees here directly. If you are interested, you can find the RASC website, and we've just noted the prices per year for membership there. So if you're a little bit interested in this, I'd suggest go take a look at the website, and you can make your own judgment on whether you'd like to become a member at one time or another. So we'll just back it up one, please. And tonight's program. So tonight, fairly full program. Sylvie Letourneau is going to do our 10-minute astronomy news. She's been alternating with our Centre President, Al Scott, through most of this year, and I'd like to thank them both for doing that. Simon Hanmer is back with talk about evidence of ancient Martian oceans. Mike Mogadam is going to bring us up to date on what's happening in outreach. We've got a lot of events, a lot of activity going on right now. Very interesting stuff. Observations tonight, and we're going to break a little bit from the normal routine for observations tonight. We won't be having as many people come up. We'll only have one or two come up, and I'll speak to most of the slides in the interest of moving along the program a little more quickly tonight. After the break, Al Scott will be recognizing some of our longtime and our youth members by presentation of pins that we've had made up. They're very nice. Al will be staying up on the podium to speak about the possibility of life on other planets. And finally, Sanjeev Sivararasa will be finishing off the evening with a discussion of astrophotography as an art form, which he's recently become very involved in, and very much looking forward to his talk. So skipping forward 2 slides, please, Chris. And so RASC Ottawa Centre members in the news. We're always pleased to see when members turn up in the news. First of all, Rob Dick. The article has to do with a satellite. I'm not sure how you pronounce that. Rob? How's the name of it pronounced? Wind2? Windy, okay. And no, it's not Rob that's windy, it's the satellite that's windy. But nevertheless, and it touches on Rob's role in design of the camera on board, if I remember correctly. Okay. Next, we also have the next edition of the RASC calendar, and Deborah and Peter Saravolo's image appears on the October page of the calendar. Okay, and the original of the image, which is a little better than the calendar, of course. Okay, next up, it's been noted that the 8th of October, I guess that's tomorrow, is it? Tomorrow is International Observe the Moon Night. I thought, in my notes I have Observe the Moon Day, but I suppose it's better to do it at night. And apparently talking like a pirate helps. Okay, so anyway, you can observe that. So, without further ado, I think it's time for Sylvie Letourneau to come up and regale us with the latest in astronomy news. Sylvie?
So good evening, everyone, and actually this is wrong. The talk is only going to be 8 minutes, and it's not about astronomy, but particle physics. Oh, excellent. That sounds really good. Okay, so moving along. Tonight I will be talking about one of the fundamentals of physics, that nothing can go faster than the speed of light in vacuum. And this is the cornerstone of Einstein's theory of relativity, and it appears to be challenged by a subatomic particle called the neutrino at CERN's near Geneva. Now, I just want to note here that this is actually not related to the $10 billion Large Hadron Collider located at that site. That's actually a different lab. So the researchers were very surprised about their results, and they have asked already others to duplicate their discovery, and there are 2 participants in that are potential. The Fermi lab in Chicago with the main injector neutrino oscillation search, or MINOS, in Minnesota. They're up to the challenge. They've already had similar results in 2007, but with a giant margin of error, so they've made or declared the experiment non-conclusive. Also, Japan is in the lead, and they could try to duplicate as well this experiment in their T2K lab, but they cannot do that yet, as this has been on hold since their March earthquake and tsunami. But here, let's look at the experiment from CERN. It is known as the OPERA experiment, and it stands for Oscillation Project with Emulsion, I'm not even sure how to pronounce that. There's my first problem tonight. Tracking apparatus. Okay, somebody can say that for me. It uses, they're busy over there. It uses a complex array of electronics and photographic plates to detect particle beams. Now, the whole thing is 1,400 meters underground to avoid contamination from other source of radiation like the cosmic rays. To give you an idea, they have already done the experiment about 16,000 times over the last 2 years before they published it, for good reasons. Also, it's important to note here that there was no beam of light racing underground with the neutrinos. the path underground is quite transparent to the neutrinos, but it would not be transparent for the light going through Earth's crust and whatnot. Also, another note before I go further, for your information, neutrinos, they're fundamental particles, electrically neutral, rarely interacting with matter, and they have a very, very small mass. They are created naturally from the decay of radioactive materials and also from reactions that occur inside stars. Neutrinos zip through space and can go through solid material easily. And as a matter of fact, billions of neutrinos have just passed through us as I was talking. The experiment at CERN was a neutrino beam was fired from the particle accelerator near Geneva, right here in Switzerland, to a lab that is 700 and, well, it says here 32, but everywhere I read 730, somewhere I read 733. Well, that could be an error, but they know the distance accurately, around 730 kilometers away in Italy. They know that with quite a level of confidence of plus or minus 20 centimeters on that distance. Now, the neutrinos, they arrive 60 nanoseconds earlier than they would have if they had been traveling the speed of light. They evaluate the margin of error on that time to about 10 nanoseconds with their GPS and atomic clocks that they've used. The run would have taken light, to give you an example, of 2.4 million nanoseconds. Okay, I'll simplify that. That's 2.4 milliseconds. So the difference of 60 nanoseconds on that is quite small. One problem with that is that the experiment is done under what would be qualified a short distance, and I think that was necessary to ensure that there was no cross-contamination. And to avoid the question that they would say, well, that neutrino that just went through my detector now, is that the one that was produced in CERN? Some scientists believe that the real uncertainty here is the travel time calculation. So if we look at the experiment itself, it starts at the top where protons are accelerated with a CERN, it's called a super proton synchrotron. Okay, I knew I couldn't pronounce that one, so there it is. And those protons, they are ejected with a magnet towards a 200 long graphite neutrino production target. So the target chamber is right here. Then they are ejected twice for about 10.5 microsecond with a 50 millisecond gap in between, and they say the beam cycle is about 6 seconds long. So when the protons hit the target, particles are produced. In that vacuum tunnel, the magic happens, and those particles decay into producing neutrinos. The question is, when exactly do those neutrinos leave the decay tunnel? The scientists use what's called a probability density function of time of emission of those neutrinos. That's a comparison between the time distribution of the proton release and the neutrinos detection. And then they seem to know the exact time, sort of. This is a schematic of the experiment, and I put that there not to try to understand exactly what happened beside that there generator. There's a target, the decay tunnel, and poop, the detection over there. But the fact that the whole thing relies on GPS, for example, to do the timestamp of the events, and that is another source of error. I've read at some places that the whole thing, they did not take into account the convention for clock synchronization in non-inertial frames, meaning the Earth is moving. Maybe that was not taken into account. There's a lot of talk about it, but where I would conclude is, well, unless, or maybe, could the neutrinos have taken a shortcut into another dimension? But for the time being, let's believe in, or I would believe in Einstein's theory and the fact that the speed of light old. And for that, I'll give you the last example of something totally different, but a supernova. When we looked at Shelton supernova, or 1987A, the neutrinos and the light arrived at different time, and that difference was 3 hours. Now, that is explained by the fact that the neutrinos are emitted as soon as the core collapses, and they can right away travel to us at the speed of light. Now, the light of the supernova is emitted when the shock wave has bounced, and then it can escape, and as well at the speed of light gets to us. Therefore, a difference of 3 hours. If the neutrinos had been going as fast as, or faster than the speed of light, like it has been proposed in this experiment, we would have seen those neutrinos arriving here from that supernova 3.5 years earlier than they did, and we did not see that. Therefore, I'm tempted to side towards Einstein once again. Thank you.
Next up, please welcome Simon Handler, who is here to speak to you about the Martian Ocean.
Before I actually start, let's make a brief comment, Sylvie. You know, there's an assumption that's been made in this business with the neutrinos. The idea is that the neutrinos interact weakly with matter. But this assumption, the assumption that's being made here for this experiment, is that the neutrinos actually pass through solid rock with no interaction. Do you see my point? This is not comparing light in a vacuum with neutrinos in a vacuum. Supposing that in fact the neutrinos are weakly, but nevertheless interacting with the matter over that 723 kilometer long stretch of crust, which of course we don't know the details of what's in that crust. We know the general geology. All that apart, I don't want to trip over here, you may well be aware of NASA's very best kept secret, which is that we are in the middle of the year of the solar system. The year of the solar system was declared by NASA in October 2010. Hands up all those who are aware that we're in the middle of the year of the solar system.
You told us last time.
I know I told you last time. I think many of you have probably forgotten. Anyway, it actually continues until August 2012. Don't worry, these international years are never 12 months long. I think because it takes a wee while for people to actually catch up with the fact that they're even taking place. Well, I decided that this would be a good opportunity to actually, for us at the RASC Ottawa Centre, to actually celebrate the year of the solar system. So I've actually got a number of talks on planetary geology in our solar system. I presented one 2 months ago about the incredible late shrinking moon. This time around, we got a different story. And the story this time is Martian ocean ? And this is yes, according to the deltas. Bear with me. So while NASA continues to chase its tail in search for water on present-day Mars, oh, and by the way, did I just move the? Oh, that's what I was looking for. Which one's center button? I don't want to change. That's just for the. There we go. That's what I want. Great, Chris. I'll ask you to change this per usual. Chasing its tail in the search for water on present-day Mars, planetary geologists have been arguing for decades about the possibility of an ancient ocean, northern ocean, on the red planet. Now, this debate started with the Mariner images of Mars from the 1970s. This is not a recent debate, when it became pretty obvious that the Martian land surface was divided into two principal terrains, as you can see. Oops, next slide, please, Chris. There we go. As you can see here, the southern highlands, here, all pockmarked and cratered, and in here, the northern plains, much smoother, far fewer impact craters. Now, the primary observation that the highlands are riddled with far more impact craters than the northern plains made it pretty clear, even in the 1970s, that the surface of much of the Martian northern hemisphere is significantly younger than that of the southern hemisphere. And the ensuing debate has focused on how to resurface the northern hemisphere after the formation of the old Martian crust, now preserved in the south. Now, there are two principal hypotheses which have captured most of the attention. The first is that the northern plains represent the equivalent of a giant lava-filled impact basin, similar to the mare on our own moon, making it, if that were the case, the largest such impact in the solar system. The second hypothesis is that the northern plains represent a lava-covered floor of an ancient ocean. Now, a recent paper in the scientific magazine Nature Geoscience suggests that we can now support the existence of an ancient oceanic-sized body of standing water in the northern hemisphere, on the northern plains of Mars. So tonight what I want to do is take a look at that geoscientific evidence, and let me tell you from the outset, it's pretty good. But before we do, let's ask ourselves the question. Think about this. How do you identify an ocean on a dry planet? Next one, please, Chris. On Earth, it's pretty straightforward. An ocean is a body of standing salt water made up of local components that we refer to colloquially as seas. The way we delimit the ocean is even simpler still. We simply trace out its shoreline. Admittedly, the boundaries between oceans are a little more complicated, but for planetary purposes, we can simply state that the Earth has an ocean, and that's it. So what's the definition of a shoreline? And I mean globally. I don't mean where's the local beach at your favorite holiday resort. Keeping it simple, we can state that all ocean shorelines occur at sea level, making allowances for tidal and seasonal variations. But this really begs the question. We come now to the real problem at hand. How, on a dry planet, do we identify sea level? Well, it's easy when the planetary surface has ocean water present, as here. Next one, please, Chris. But how do we identify sea level if we take the water away? Don't be fooled by this image. What this shows you here, and these are garish reds and greens, those are the continents, and the blue here is our ocean floor. Don't be fooled by this image. Look at it through the eyes of interstellar aliens at some time in the distant future who are still trying to figure out if Earth ever had an ocean in its history, its earlier history. Suppose these aliens were highly skeptical. What would it take to prove to them that these blue lowlands, these blue lowland plains in this image, were once ocean basins? The traces of plate tectonics in the basins, such as the mid-ocean ridges you can see here and there, or the transform faults, which are difficult to see, but they're there in this image. There we go. You can see them quite nicely here, at a high angle to the mid-ocean ridge. Or the alternating symmetrical magnetic stripes, which are not present in this image. These tell you how the basin formed, but they don't tell you anything about the presence or absence of water. Enough water to fill those basins and turn them into real bona fide oceans. So what evidence do we need to actually convince the aliens? We need deltas. And by the way, for those of you that don't know, the way that our modern oceans form is by continents actually pulling apart. And then these large volcanic centers here in the middle, they actually are what create the ocean floor that we now see today. Next one, please, Chris. So what's so special about deltas, you might ask? Well, to answer that question, we have to look at what they are and how they form. So let's do this in 8 steps. Think deltas anonymous. My name is Simon Hanmer, and I'm a deltaholic. Step 1, rivers flow, and some flow to the sea. Step 2, rivers carry sediment, that's sand and mud to you, while they are flowing. Step 3, when river water reaches the sea or ocean, it hits but what is by definition a standing body of water. Step 4, from the river water's perspective, it just hit a wall. So it slows down and it stops. Step 5. As the river water loses speed, it loses its ability to carry the sediment and drops it on the sea floor immediately adjacent to the shoreline. Step 6. Because the river water is slowing down at the shoreline, the main river channel divides into a braided system of channels in order to evacuate the same volume of water in the same time as the water is headed downstream in the main river channel inland. Hence, the river system now has a delta shape whose pointy end points back up towards the river system. Step 7. When the braided river drops its sedimentary load, those sediments will also have a delta shape, which will survive even if you remove the water at some later stage. And finally, step 8. Rivers, by definition, tend to meander. They swing from side to side when they're flowing slowly, which means they change physical location. So it's no surprise to see that a real delta like the Mississippi has built up as a series of deltas that overlapped and piled up on top of each other in different locations over time. And the time we're talking about for the Mississippi Delta is about 10,000 years. Now, these 8 steps in delta formation lead to an obvious conclusion. Deltas, by definition, mark local sea level. And a series of deltas of about the same age will mark locations of the same sea level over a wider area. And because deltas are accumulations of riverborne sediments, they will mark sea level even in the absence of water, the water associated with their formation, including the sea or ocean that they've formed at the edge of. So I think you can see where we're going to go with this on Mars. But let's look at a couple of terrestrial deltas first. Next one, please, Chris. Here's the Nile Delta. There it is, nice and triangular. It's about as classic as it gets. It's located at the north end of the Nile River in Egypt, where the Nile River meets the shoreline of the Mediterranean Sea. Unlike the Mississippi Delta, which is made up of a series of smaller deltas of different ages, this is a single long-lived accumulation of sand and mud, and that's why it retains its classical delta shape. Next one, please. Now, this is a false color image of the Lena Delta in Siberia at the north end of the Lena River. The different colors correspond to different sedimentary materials that make up the fan-shaped delta. Again, essentially sand or mud. And here you can readily see that over on this side, there's the Lena River, by the way, going down that way. This side here of the delta, you can readily see the active braided streams that are confined to the east. While the isolated round lakes that you see over here, lakes and ponds to the west, they're located in an older, currently abandoned part of the delta. The point here is that deltas are not static. They're very dynamic things. They evolve through time. Next one, please, Chris. So now let's return to the Mississippi Delta in the southeastern US. And as you can see in this satellite image here, and the accompanying inset, so this corresponds to this, this delta does not have a simple fan shape. Next one, please, Chris. There we go. The easiest part to identify is the currently active delta. You can see how it looks like a bird's foot. That's actually the technical term for it. It is a bird's foot delta, surrounded by submarine sand, that's the yellow stuff here, which has been deposited by the river. Next one, please, Chris. Now, if we outline the successive components of the entire Mississippi Delta, there's the current area here, and the numbers here refer to the time at which these various components formed. You can see that the entire Mississippi Delta was built up over time, and we can see how it's a composite delta made of many fan-shaped components, and that the bird's foot is just the latest manifestation of delta construction. Okay, very nice. So what has all this got to do with the occurrence of ancient oceans on Mars? Well, the question really is, are there deltas on Mars? And can we identify them? Next one, please, Chris. And here, the answer is a resounding yes. The Earth version here on the right, and the Martian version here on the left. So for good measure, what I've done here is I've juxtaposed the Indus River Delta in Pakistan with part of the delta from the Holden Northeast Crater on Mars. And the Holden Northeast Crater is located off the open end, the eastern open end of the Valle Marinaris, for those who know. Now notice how both have an overall fan-shaped structure in which we can see the traces of multiple river channels. There's a really obvious one there, but look, there's all kinds of river channels over here. And here I think you can see the traces here of river channeling there too.
Simon, are they the same size?
Coming to that.
Oh, sorry.
Now, and in both cases, these were built by water flowing in from the left with respect to this image. In the Indus example, those channels are low standing and they're actually filled with water today. But in the Martian example, they're actually high standing wiggly ridges made of consolidated sand and gravel that resisted wind erosion that has removed much of the mud that was laid down between the river channels. So what we've actually got here is the negative image of a delta, represented by ridges rather than channels. Now note the absence of scale bars, because these deltas are not the same size. The Martian one is much smaller, but that actually doesn't matter, because the important thing from our point of view is we want to establish here whether delta-forming processes have occurred on Mars, whatever the scale, and they clearly have. Next one, please, Chris. Now, this abstract-looking object is a perspective rendition of the complete Holden northeast delta, which is also known, if you ever come across this, as the Eberswald delta. Why? I'm not quite sure, but it is. It turns out that only the northern part of the delta up here has a classic delta shape to it, or fan shape. The rest is more a series, here, 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 here. A series of bird's foot shapes, very reminiscent of the Mississippi Delta on Earth. And they probably built up through time. Next one, please, Chris. And here's another example of a Martian delta in Jezero crater. It's located just east of Syrtis Major, for those who know. And it's got a false color component here to highlight the different kinds of sediment. Again, sand and mud mostly. This is an intriguing combination of a classical fan-shaped delta, which you can see here, but it's been overprinted by channels going up through there and coming down through there, channels which have actually left bird's foot features. So again, a dynamic kind of delta, the kind of thing we've seen on Earth. Now, I've shown you these two Martian deltas because they're the ones for which I could find the best quality images. But, have you noticed? They both occur in craters, which means that they're deltas that formed along lake shores, not the shores of an ancient ocean. That's not a problem for us, though, because I wanted to use them to show you that delta-forming processes have occurred in Martian geological history. Next one, please, Chris. So here we change scale completely. This is a map of planet-scale distribution of Martian deltas, which was used by the authors of the Nature Geoscience paper. The red squares represent, that's these things here, there too, and then there. The red squares are interpreted to represent deltas interpreted to have formed at the margin of the Northern Plains Ocean. And altimeter measurements show them to sit at heights within a few hundred meters of each other, which by Earth standards is actually pretty good. Believe it or not, sea level on Earth doesn't occur at one level. It actually occurs within a range of altitudes. In other words, these things do indeed mark ancient sea level. They are actually of about the same age. The other symbols, the blue ones, they represent deltas which formed within craters. In other words, they're deltas that formed in lakes. Now, the fact that only 1/3 of the known deltas appear to be associated with the boundary of the Northern Plains might explain why the best images available on the internet right now from NASA are the images of deltas that formed within craters. Nonetheless, the red squares do appear to trace the boundary of the limit between the Southern Highlands and the Northern Plains, except around the northern part there of the Tharsis Plateau, or the Tharsis Uplift. I'll come to that in a second. Next image, please, Chris. That's an interesting observation, the lack of the deltas around the northern edge of the Tharsis Plateau there. And this is also showing up in this diagram, which is of the distribution of the density of river channels within the highlands, within the Southern Highlands. And the highest densities are indicated by the yellow and red colors. You can see them through here and over there. The northern limit of the channels represents rivers that did not necessarily form deltas, but reached the Northern Ocean and ended. Notice how the northern limit of the channels corresponds to the Southern Uplands, Southern Highlands, Northern Plains margin, except here, just north of the Tharsis Uplift. So this perturbation, if you will, in the distribution of deltas and river channels around Tharsis tells us that the highland-lowland boundary in this region here, is actually the result of the Tharsis Uplift itself. The fact that it's a plateau means there's been uplift. And that has then disturbed the boundary between uplands and the lowlands, rather than it being an undisturbed ocean shoreline. Next one, please, Chris. So, for the time being, it would appear that the Martian ocean hypothesis is once again in the ascendant. As Napoleon's mother said, pourvu que ça dure, which means, let's hope it lasts. Next one, please, Chris. And this is my final slide. But let's keep this likely Martian ocean in perspective. Earth is relatively large and endowed with sufficient water that 75% of the planet is covered by ocean. Mars itself is much smaller than Earth, and we're talking about a smaller ocean covering only about 1/3 of the planetary surface. More importantly, we know that ocean basins formed on Earth as continents split and drift apart in the global process known as plate tectonics. On Mars, we do not have a clue. I can't emphasize this too much. We do not have a clue as to how the northern plains might have formed as an ocean floor. And the issue is all the more complicated by preliminary observations that the material beneath the northern plains might be identical to the southern highlands, including impact cratered to the same degree, which would be the very antithesis of plate tectonics. In short, planetary scientists are making good progress in understanding the geological evolution of the Martian surface, but they've not got it all solved yet. Thanks for listening, and happy year of the solar system.
Thank you, Simon. Very illuminating. Next up, we'll have Mike Mogadown to fill us in on public outreach activities for the century.
Hi, everyone. I wanted to mention something I just learned just about 10 minutes ago. Jacob von Kors, you're here. Can you stand up, please? So Jacob, 14-year-old, took a picture that is in Sky News. It's in the newest edition of Sky News, latest edition of Sky News. It's just coming out now. You should all get it in your mail in the next week or so. I got a couple issues that just came in for outreach. But Jacob took a beautiful picture of the Pleiades. That's, I guess, from Nirvana. Is that when you took it? Okay, well done, Jacob. That's awesome. That's terrific. Good show. Thanks very much. Okay, first of all, by the way, another thing I wanted to mention is thank you so much for all your help assembling the planisphere. That's a tremendous amount of help. It really got me a long way, so thanks so much. So Science Fun Fest, it's the outreach event of the year. It's a blockbuster event. This year we're expecting about 8,000 people. I think I know I've mentioned this a couple of times now. This is our third year that we've participated in Science Fun Fest. It's an event that's organized by Natural Resources Canada. It's an event very much suited for generating interest in science for kids and maybe spark and potentially spark a career in some field of science. There's a lot of interactive exhibits, hands-on exhibits that are presented by various groups of the government, including our group as well, and some other non-governmental groups. Next slide, please. Here's what the RASC is doing at FunFest. We got a bunch of different exhibits, as you can see there. We're trying to sort of make it very interactive and engage a lot of discussion with people. One thing which is new this year is that last year we had a planetarium courtesy of a private company. Sadly, the fellow that provided the planetarium, his business went under. I think I may have mentioned that in the last meeting. So this time the museum is joining us. Science Technology Museum is joining us, and they're bringing their planetarium. So I'm very, very grateful for that. The planetarium that we had last year was a big draw. Okay, and by the way, if you were actually at FunFest last year, there was huge lineups. Okay, and we were thinking we can't have those lineups because it was kind of discouraging. So the museum actually said, well, why don't we? One way to avoid those lineups is to have a sign-up sheet, kind of like the Disney and the Universal Studios style, where you kind of arrange the time you'd like to attend the planetarium show. So this will work a lot better, and I think people will be a lot happier. But the usual thing we have is indoor exhibits. Weather permitting, we'll have solar observing, and even if it's cloudy, we're going to have some outdoor. We're going to look at distant objects on buildings and so forth. So next slide, please. Okay, so for those of you who don't know, it's Science Funcast is located on Booth Street and Carling. Okay, right on as you can see right on the map there. Sunday, October the 16th, 11 to 4. That's the public time. If you're volunteering for this event, and I'll talk about that in a second, I'll need you to come a little bit earlier to set up. They close off a bunch of streets around this area. It's very big. There's a lot of indoor exhibits and in various buildings, as well as exhibits in tents throughout the area. Yeah, so the parking, there's a couple of places to park. It's not a lot. Right off of Rochester Street, I believe. I will, just going to walk over here.
There's a public walk.
So Science Fun Fest is all along, actually this circle here is a little off. It should be right here on Booth Street. And so sorry about that, it's off. There is parking just in this area along the side streets. It is free, but there's not a whole lot of parking. So my recommendation is if you want to get parking, you want to be there a good hour in advance. And in fact, they close off Booth Street at 9 o'clock. So it's big.
Mike, there's a large car park. It's a paying car park. There's a large car park at Beach and Preston. And there's another large car park just off Dow's Lake, essentially where Preston ends at its southern end.
Right there.
Yeah. No,
Can you move that red circle over? So it goes around Booth Street?
Can you move the circle?
Yeah. So sorry about that, the circle is a bit off. So it sounds like there's a couple of parkings. Are you sure it was off? Yeah, so it sounds like there is a couple of parking lots in the area. I think you might have to walk a little bit, right, Simon, though, if you were to...
Oh, no, you're from Beach, you're walking 50 meters. And from the one at the very southern end of Preston, you may be looking at a couple of 100 meters maximum.
All right. Well, thanks for that. Okay, so if you want any more information on that, contact the following folks. Next slide, please. I've got a bunch of volunteers, and I'm also looking for a couple more people. Next slide, please. So I could use 2 more people with solar equipment. So if you are able to, okay, if I can get your name afterwards, please. And planispheres, the ones that we've been assembling, they go like crazy. Okay, they're like hotcakes. So people, they come and they take them. We hand it out, and they always ask a question. So I'm looking for 4 people to do that planisphere support. We explain what it's all about, what it does, and so forth. And I need 2 more volunteers. So you don't need to volunteer the entirety, 11 to 4. Maybe you have a couple hours that you want to volunteer. That'd be great. If you sign up, and I need to know tonight, okay? Because I have to get back to the Fun Fest organizers by Tuesday morning. You get a free lunch, you get a T-shirt, you get my thanks, and fun. Okay, so Fun Fest is great. Lots of interaction. It's just wonderful. Okay, next slide, please. Okay, another event which we've been, another National Science and Technology Week event is offered by the museum. It's Terrence Dickinson has been invited to offer a lecture on simplified stargazing from city or country. And that starts at 7 p.m. on Friday, October the 21st. So I guess that's 2 weeks tonight. Wow. And the museum has also asked us for if we could bring some telescopes and help with a star party. If there's clouds or rain, obviously it's a no-go. There's not even any backup rain date. But like I mentioned in previous meetings, the museum events are getting better and better and better organized. So they're getting a larger number of people. Obviously, they're promoting a lot. In the last couple of museum events, we've been overwhelmed. So I'm looking for 6 people with telescopes. And even if you don't have a telescope but you want to participate and maybe mingle and answer questions, that'd be great as well. But you know what, if you could nab me at the break and let me know if you're interested, because I really need to confirm with the museum as well. But again, I'm really surprised at how museum events are getting lots of many people are showing up for them. Okay, and by the way, if you're attending that Terrence Dickinson lecture, you got to sign up on the web. It's actually, I think, right in this room here. Yeah, sign up on the web, and it's free. So if you go onto the museum's website, you'll find the lecture and the free sign up and so forth. Okay, next slide. Next slide. Okay, last thing is the CARP. We have our final CARP public stargazing schedule, public observing. It's Saturday, October 22nd. There is a rain date. Next slide, please. We are located, we observe at the Diefenbacher site, right adjacent, it's a CARP, the parking lot of the CARP branch, the Ottawa Public Library, right adjacent to the Diefenbacher site. We'll put this map up after the meeting, and I'll be around if you want to have any questions about where and how you get there and all that stuff. Okay? And it's free. Open to all.
Okay, Mike, you can stay up for one more slide that you don't know about.
Okay. Oh, jeez. Go figure. This thing doesn't work. Yeah, there's jackets obviously I'm selling. So tonight is the last night order. Yeah, in your dreams. Okay, I'm done.
There we go. And thank you, Mike. Okay, we're going to go straight into observation reports. And as I mentioned earlier, in the interest of time, I'm going to speak to the slides tonight rather than calling people up. So we have a fairly full slate. We'll get a couple of people to speak, mostly because I didn't want to speak to their particular images. But other than that, a couple from outside the center, Paul Commission, Tom Butterworth, Gordon Webster, Bob Olson, Gary Boyle, and Rolf Meyer. So just to start off with, seasonally, there's been some debate over the last little while about whether there actually is a Turkey nebula or not, you know, Thanksgiving time and all that. There's been a lot of talk on the web, and there have been a few images turn up. So the debate right now is which one is the true Turkey nebula. So we've got the first one here, which is fairly convincing, but yeah, it's a little questionable. It might be some dirt on the lens or something, I think. Yeah, okay. The second one is more familiar, and you know, if we look hard at this, it does have a little bit of a look like a bird, doesn't it? Yeah. So happy Thanksgiving, everyone. Yes. Okay. So next up, I think we've got Paul Commission. Paul, would you like to speak to these?
Yes, I'm showing 3 Berkeley clusters. These Berkeley clusters are not that bright, but they're visible in a small telescope. They're all located in Cassiopeia, which is now quite comfortable for observing. And I thought I'd show these because there was a lot of controversy over these. The 3 that I'm going to show you are clean. That is, they're new. Some of there's 1 to 104 of them, and many of them were claimed by other people like Ivan King. Well, Trumpler was dead then, but some of them were Trumplers. It was a great controversy. But this fellow named Weaver took 104 of these photographs of these clusters, and the 3 I'm going to show you that are in Cassiopeia are the best to observe with a small telescope. If you want the coordinates, come and see me after I've got them. So just go through the 3, please. That's 5. This is 6. Next one. And there's 7. And these are not claimed by anybody else. They're real Berkeleys. Thank you.
Okay. Thank you, Paul. And interestingly, for you know, people looking at those, and you don't get a good feel for how faint some of that stuff is. I did a little looking into the Berkeleys, and in particular, the first image that you were showing, Paul, the brightest star in that cluster is Mag 17, correct?
No, I think they're about 15 or so.
Okay.
The dimmer ones are around that. But that cluster is quite visible in an 8-inch. A C8 will show it to you.
Okay. Thank you, Paul. Okay. Next up from Tom Butterworth. He provides a very nice image of M31, and he states this is a first light image from his new observatory location. This was done with a William Optics FL132. Somebody's got some money, I guess. On a CGE Pro mount. Somebody's got even more money. With a Starshoot Pro 6 megapixel single shot color, and auto-guided with an Orion AG. It's an 80-minute exposure minus 20-minute dark master, no bias, no flats. So pretty nice job, I'd say, for a first light image. Next up, please. Thank you. Next one up, we have a series of sketches by Gordon Webster. The first 2 here are sunspots observed in September 2011. The first sketch was made around 5 p.m. DST, Sunday, September 18th. He scanned it, so he does his sketch, and then he scans it, and he adds color so you can see the white areas at the eastern edge of the sun, which I think you can just barely see there on the eastern side. He has a photo that he downloaded from the web, taken on the same date. It shows similar placement of the sunspots, and you can see he's enlarged the spots a bit in his sketch. So I don't know if we can flip back and forth, but you probably saw the fade. Oh, great. Okay, so if we see it now, transition, they're pretty much in the same place. You can see he's enlarged the spots a bit on his sketch. It's an effect of the closer attention you have to pay to what you're observing when you sketch it. So it's kind of magnification due to paying close attention. Okay, next up, very nice. I'm not sure how to pronounce this. It's V. Aquile. I don't know if it's actually supposed to be pronounced V or there's something else. Just letter V. Okay, he says a wonderful orange-red carbon star in Aquila near M11. So you can probably see the one very red star there. Very nice job there. Image 4 is OEE1 Otto Struve supplement. First double star in the Otto Struve catalog supplement. It's located in northern Cepheus near the border with Cassiopeia. Okay, a nice color variation between the two. At least I'm seeing color difference in there. Okay, again, very nice. Image 5. Okay, NGC 7023 is a reflection nebula in Cepheus, also known as the Iris Nebula. He says he was using his 120 millimeter refractor with a go-to mount, and this is what he saw. When he when he looked away to see other stars in the field, suddenly there was a nebula in averted vision, which is image 6. So can you see the nebula drawn in? Yes, very nice. I tried it several times with other stars in the field, but only the center star responded. Thought it was a good example of the power of averted vision. So that's the last one. Very nice job there, Gordon. Well done. Okay, next one up, Bob Olson, perennial favorite of ours. So he starts off, so a little bit of a story here. Bob relates that the moon was up, so he decided to use hydrogen alpha filter for imaging to cut the sky glow. It's kind of not in the order I would have expected, but the lunar image here is actually shot in hydrogen alpha. It's interesting to see the amount of detail and sharpness he gets, especially in the lower quadrant here. The craters come out very nicely. I felt myself it looked somewhat more blurry up here, but not sure if you see the same as I do. But anyway, the close-up, if there's a close-up, is just a crop of the same image to show the detail a bit better. But really very nice detail here. It's interesting. I don't think I've seen anyone image the moon in hydrogen alpha before. Next up, oh, we're not done. Save it. Okay, M42. And as he says, he was looking around for red objects to image, and he spent several days doing so while the moon was up. When the moon was down, he then grabbed some red, green, and blue images to create his hydrogen alpha RGB images. So he says he's new to narrowband imaging, so he had a hell of a time with color balance. The M42 image is not color corrected, but it does look kind of neat. And some interesting and unusual detail to be seen in it that you wouldn't normally see in an RGB image. Now, is there another there, or is it? Yes, and there is one more. And a nice red object there. I love the luminous blue up in here as well. Comes out beautifully. Very, very nice. Is that the last one now?
Two more.
Nope, two more. Okay, the bubble nebula again. Nice red object, and the bubble came out very clearly, very sharp. And lastly, Sharpless 2-155. Not one that I'm familiar with, but a very interesting looking object. All right, very nice job, Bob. Okay. And next up, we have a couple of images from Gary Boyle, apparently shot from Peggy's Cove in Nova Scotia. I was struggling for the name. I've been to this point a couple of times myself. A very nice sunset image of the lighthouse on Peggy's Cove. Next, please. This one, he says a 30-second exposure shot from the lighthouse base. This, of course, is the lighthouse you're looking at from down below. He says he used a cell phone to illuminate the lighthouse.
Yeah, this one right here, just a few seconds, just to make it glow just a little bit.
There you go.
On that side, it actually lights with the parking lot.
Very nice, Gary. You had the camera on a tripod, of course.
No, really resting on a rock on a...
Really? Came up pretty well. Didn't joggle it.
Is that a red star or a red light just on the left side of the lighthouse there?
Could be a pixel. No, that's part of the lighthouse. That's off.
That's probably just the edge of the lighthouse, huh?
Yeah, just the edge.
Yeah. Very nice, Gary. And was that our last one there? Yes, we have. Okay, and this one of Gary's was a Jupiter shot with EO, whichever you prefer, on the right, and Europa on the far left over here.
First time I ever got color.
Really nice. Yeah, on the moons, huh? That's interesting. Very, very good. Okay. Let's see. And now Rolf has a few observations. He should be right here because he wasn't going to delay things.
From here,
All right.
save a few seconds.
All right.
This was taken with the program that Eli talked about a little while ago, the backyard EOS program that he has developed. And so these are, the one on the left was the first one that I did with the 6-inch and 9.5 of the C14. And not too bad, so you can use your DSLR for planetary imaging as well. Next, oh yeah, well actually, go back, I should just point out the great red spot on the left image and the small red spot on the right image.
Is that the small there?
That's right, that's the small red spot. Now these have south at the top, and I'm going to show another picture that has them upside down. But anyway, the next one here, so at Canadian Tire, they have these telescope covers. So if you have anything from a 12-inch to, say, a 25-inch telescope, these are great telescope covers. But you get 4 in a package. For some reason, I guess, because there's 4 tires, but so for $30, but these are actually on sale for $22, so you get loads of telescope covers.
Very nice.
That's my observation of the moon in that part of that one. Okay, so next, so this is with C14 again and the planetary camera with Fleet 3. And this one you can see is got north at the top and then a small red spot at the bottom. The small red spot.
Oh, yes, sorry.
Yeah, there it is. And the next one, and this one shows the great red spot. Again with the north at the top.
Okay.
That's it.
And the last one, thank you, Rolf. Very nice job. So,
Oh, I forgot to say something.
Huh?
So that was actually taken on the night of the star party, and people were observing Jupiter that night, and I think they all remarked on how good the scene was that night.
so it would appear from that image. Very nice, Rolf. Okay, next up. So just a couple of service announcements before the break. First of all, Rob Dick is holding his annual observing weekend or get-together at his place. You can see the dates here, the 21st and the 22nd. Very nice piece of equipment out there. If the weather is good, it's always a very nice time, and if the weather's not good, it's still pretty fun. A bit of a gab fest and get together for dinner, that sort of thing. So if you're interested, you can either talk to Rob during the break or after the meeting, or alternately, you can contact him at his email address at the bottom here, rdick@carleton.ca. So anybody interested, do get hold of him. I've been down once or twice and very much enjoyed myself. Next, please. Okay, I just wanted to mention here, it will be mentioned later in the evening, but one of our members, Sanjeev Sivararasa, is having an exhibition of astrophotography images at the at the Cube Gallery. I can never remember the name, but at the Cube Gallery, Sunday, October 30th, from 2 to 5 p.m. And I'd invite you all to go on down and see the show, support one of our members, and I'm sure he'll mention more about that a little later in the evening. Next, please. Okay, as well as that, our annual dinner is coming up on November 18th. Our guest speaker this time is David Saint-Jacques, one of our CSA astronauts. Gary Boyle has got the tickets here this evening, and you can see him. He's right. I was going to illuminate you with the laser, but no. Yeah. Okay, but he's right there. So you can see him to get tickets tonight. It's a pretty good dinner, and usually an interesting talk. Lots of good times. You can see Deborah was very pleased with the ice carving. You should have seen the backside. The back of the fish is what she's laughing at. But anyway, but is it? The School of Cooking puts together the spread. It's very good. It's very good for the money. So having attended last year, I'd say go by all means. Anyway, next please. And again, the jackets and the handsome model here. You can see the handsome model outside and sign up for one of these if you're interested. This is the last night for ordering them. All right. Next up, the center president, Mr. Al Scott, will be up to present membership recognition awards, pins. Welcome, Al.
Hello, everybody. Welcome again. I mentioned I started this last meeting. I'd like to have this program to recognize members, people in long standing who have supported the club for many years. So we started a program. We designed some little lapel pins, and we would like to hand them out to people at various anniversaries of membership in the Ottawa Club. Last month, we recognized Service Award recipients and our one 60-year member. This month, we'd like to recognize a couple different groups at both ends of the scale. I'd like to recognize our youth members first. Something that we'd like to encourage is to get the youth interested in the club. So I've actually had a couple pins made for youth members, and we'll start off. What I'll do is I'll announce your name, and if you're here, you can come on up and I'll give you your pin. And if you're not here, we'll also announce you at the annual dinner if you're available then, or we'll mail out the pins. So for youth members, we have 2 youth members, and I think that's under 21 and under, or under 21, I believe. Mr. Jacob Von Koris is here this evening. I had an image highlighted already. Let's find your pen. Jacob. Congratulations on your image. And Nicholas Zuger, who could not be here this evening. This is something we can work on with our outreach and increasing the number of youth members in the club. Next, we have 50-year members. These are members who have been with the club for 50 years, or between 50 and 60 years. First, Dr. Hugo Lama. We have joined us in 1954.
For youth members, I could say I started when I was in grade 8. That's why I got 50 years. Back in Toronto, we had about a dozen to about 20 people showing up at the meetings, and that's big city of Toronto. And the main preoccupation seemed to be at that time to go down to the basements and grind your own 6-inch mirror, walk around the barrel. So as you can see from the images you've seen tonight, you've come a long way. A
lot of these members actually joined when the NRC was here. The astronomical group, the HIA professional members joined the RASC back many years ago, as there was not a separate professional organization, and this was the professional organization of the Canadian astronomers, and many of them are still around. Dr. Victor Gaizauskas, I believe, he wasn't going to be able to be here this evening, I don't think. Mr. Gordon Grant as well is an Ottawa resident but was not able to attend. Ms. Mary Henderson? No? Okay. A lot of these members don't like driving at night as well, so some of them do come out to the annual dinner though. William Day, Mr. William Day? There we go. Excellent. Thank you. Thanks. Mr. A.A. Griffin, I doubt he'll be here. His address is Vancouver. We have several of our longtime members, they used to sell life memberships. So several people have moved away but are still associated with the club and keep in touch through the Astronauts publications, for example. Dr. G. Lindsay. Okay, we're getting up, Dr. Lindsay joined in actually 1960, so we're getting closer to the end here. There's a Mr. R. Salmon, also probably not here, his address is Hawaii. And Dr. Lloyd Higgs, who I already sent his pin to, he's also out in Vancouver and can't come. And Dr. D. Smelly, I don't think he's actually, okay. All right, well, thank you very much. For those of you that were able to come, we'll move on to the next one now. So, call for volunteers. Our longstanding editor of Astronauts, Deborah Cervolo, is moving on to other things, and we are looking for volunteers. And if you enjoy your Astronauts online publication, you can step into the role and continue it. And if you don't enjoy it, then just you can come up and fix it. So we're going to start arm twisting if nobody steps forward. So please come and see us after the meeting if you have any interest in publication or online news gathering. Okay. And now on to my talk. So this is a talk I actually originally gave at the Cube Gallery earlier in the year. They sponsored something called Nuit Noire, where they were celebrating the night sky, and they asked me to come talk about the possibility of life on other planets. And I thought it was really an interesting talk, and we generated a lot of good discussion there. And I thought, well, this would be great for the members here to hear. And if you're at that talk, I'm sorry if there'll be some duplication and overlap, but hopefully you enjoyed it that time. So the question is to look at the possibility of life on other planets. And when you ask this question, it's not really clear what you're asking, because a lot of people think of different things when you ask this question. Life on its own could just be single-celled amoebas, bacteria, archaea. But a lot of people, when they ask this question, are thinking of intelligent life. But there's also a difference between intelligent life and, say, self-aware life. We know that there are a lot of different species on Earth that we would consider intelligent, but maybe not self-aware or able to communicate. And other people, when they think about this, think about advanced civilizations. And some people even think about UFOs, which is a bit of a stretch in some terms. And then the other question we have to ask is, if you want to address this question, would we recognize life if we found it? Or advanced life if we found it? Maybe advanced life is all around us and we don't even know it. How would we tell, especially if it's not communicative? It has to be somewhat gregarious to actually carry on a conversation at a level that we could understand. So, to understand the possibility of life in the universe, we have to understand a little bit of the history of life on Earth. So this is a useful graph that kind of shows you the history as we know it of the life on Earth. And the Earth formed about 4.6 billion years ago, along with the rest of the solar system. And not a lot happened for the first little bit. It was pretty boring. The moon was thought to have formed right near after the Earth formed by a collision with the Earth and then accretion in orbit. And there was a period from here to here called the heavy bombardment. Basically, there was a lot of rocks in the solar system, and they kept pounding down on the Earth and Mars, and there were planetesimals forming and colliding. There was a lot of cratering. All the craters on the moon and the Mars that Simon was talking about earlier occurred in this period up to the end of the late heavy bombardment. And people can date surfaces depending on how many craters they have, or the density of craters from this, mainly from this period. And the Earth was thought to be relatively inhospitable during this time because a lot of these bombardments actually melted the surface and sterilized it completely, especially the one that created the moon. So, and then we have a long period here. We have the Hadean and the Archean periods, and we have evidence very soon after the late heavy bombardment of the appearance of life on Earth. And we see this in fossils in the rocks for biological processes occurring in the rocks themselves. And we know that photosynthesis started somewhere around 3.5 billion years ago. The atmosphere back here was thought to be, there was no free oxygen in the atmosphere at this time. Free oxygen in the Earth's atmosphere was created through the process of photosynthesis from the bacteria and the archaea, I should say, in the oceans. And they basically turned the atmosphere over this period from reducing to oxidizing around this period. This is around the first time that the atmosphere was oxygen-rich as we would recognize it. So during this whole half of the Earth's existence, we couldn't have survived on it. And then after that point, you start seeing evidence of the first complex cells in fossils, eukaryotes, and then multi-celled life appears about here. And as you progress, more advanced forms start appearing, and then we see humans appearing right about there. So a lot of our questions on the likelihood of advanced life in the universe are based on this sample of one, shall we say. And so if we think about the probability of at any particular time encountering an intelligent species that might be able to communicate on the Earth, you can see that the percentage is rather small. So from our sample of one, we see that there's not a great chance that if you came to the Earth at any particular time, you would find anyone who could talk to you. There's a lot of things also that happened that allow this. As Simon mentioned in the earlier talk, Mars used to have an ocean. Earth still has an ocean. Why does Mars no longer have an ocean? Mars is now a relatively inhospitable planet. And the reason, we think, is that Mars does not have a magnetic field around it to protect it from the solar wind, which basically wiped the atmosphere out into space and the water all dried up. Earth has a magnetic field because it's big enough to maintain a liquid core, and possibly due to the influence of the moon and the tides keeping the Earth, pushing it and compressing it, this actually generates internal heat and may have kept the core molten. So maybe we need to have a big moon to actually maintain a magnetic field long enough to have an atmosphere for life, for intelligent life to evolve. These are questions we don't really know the answer to. You need a star that's not going to have mega flares and irradiate the planet and completely wipe out all the life. You can't be too close to a supernova that goes off in your general vicinity and ionizes the atmosphere and kills everything. So we've been rather lucky over the last several billion years since the evolution of life that the Earth hasn't been completely sterilized, or not that we know of anyways. You need liquid water to act as a medium for the metabolism and chemistry to appear and evolve. So there's a lot of prerequisites that we think are necessary for life to evolve on Earth. This is the Drake equation. Some of you may recognize it. It's commonly trotted out when people talk about the probability of life. And what it is, N is the number of civilizations in our galaxy with which communication might be possible. And what you do is you multiply together a bunch of factors that are fractions between 0 and 1, except for L in the end and R at the start. R is the rate of star formation. L is the length of time for which a communicative civilization exists once it evolves or arises. And then we have all these fractional things. And really, we don't know much about any of these terms. We're just starting to learn about some of them. Well, actually, we do know very well what the average rate of star formation is in the galaxy. We are starting to learn about this. In the last 2 or 3 years, we've started to really discover planets around other stars and have the tools to look at them. But before the last 2 or 3 years, anything you would say here would have been a guess based on a sample of 1. The average number of planets that can potentially support life per star. We really don't know anything about that. We can guess. We can make some educated guesses, but you can put any number there and people would nod. The fraction that go on to develop life at some point, nobody knows. The fraction that actually go on to develop intelligent life. Nobody knows if you have life, whether, excuse me, if life evolves, give me a second. Oh, that would be nice, thanks. Sorry.
Pure water.
Whoa, good stuff.
I tried that.
All right, so where was I? So nobody knows whether advanced life will actually evolve once you start out with life. It's not a smooth progression. You start with life, but you may wait 4 billion years for intelligent life to appear. So, the first place we want to look for life is on the other terrestrial planets in our solar system. These are close by. We've had some time to look at them with our robotic probes, with our telescopes. And over the past 10 years, we found that life can evolve or can survive in very harsh conditions. 10 or 20 years, we've started to search. The field of astrobiology is relatively new, and people are starting to look for what are the extreme conditions where life can actually survive. We found life on Earth, for example, in boiling pools of acid. We found it in nuclear reactors. We found it frozen in glaciers. We found living cells buried deep in bedrock. All other solar system bodies which we've explored appear to be barren of life, though. The moon is pretty well devoid of water, except for some recent evidence of permafrost buried in permanently shadowed craters near the poles. Mars is expected to have extensive subsurface permafrost, but there are currently, and perhaps for several billion years, there have been no long-standing bodies of water on the surface. Venus, Earth's warmer twin, is actually relatively dry and is shrouded in sulfuric acid clouds. And landers have shown a barren, hot surface. There are some hints, though, that life may still exist, or at least there may be expectations that we could find fossilized life on some of these places. Mars, for example, may have had an ocean which may at one time have harbored life, primitive life at least. There has been detections of in the Martian atmosphere of methane. And methane is not a stable chemical on its own. It breaks down relatively quickly, and it's formed by living processes. It could be created by microbes that are still surviving in the permafrost below the northern hemisphere. Or it could be coming from volcanic vents and then breaking down once it gets into the atmosphere. We know that there are entire ecosystems that have been discovered in the last 20 years in the bottom of the oceans of the Earth around sulfur vents, hot sulfur vents with volcanic material are actually spewing chemicals into the water, and life is existing by metabolizing these compounds rather than using sunlight as their prime source of material. And this may have been how the original life formed on Earth. The original life, when there was no oxygen in the atmosphere, could have been a chemical process. It's very possible that life could survive if seeded into some of these areas. Some of these extremophiles could survive in permafrost, or perhaps floating in the clouds of Venus metabolizing sulfate. Interesting questions, and be very difficult to find them because they certainly wouldn't exist in very large amounts if they were there. And then the icy moons of Jupiter are an interesting potential source of life. This is Europa. Europa is an interesting moon. It's an ice moon of Jupiter, and it's crisscrossed by these stripes, these red stripes, and the red material there actually is got organic chemicals in it. And what they think is that below the icy surface of the planet there is a briny ocean, or of the moon, I should say. There exists a briny ocean, and these chemicals well up in cracks in the ice. And there could be life in these oceans. And these moons are warmed by tidal heating from orbiting Jupiter, for example. And that may be keeping these oceans warm. So scientists are thinking about sending missions to actually explore these moons. And even there have been talk about developing a nuclear-powered drill to melt through the ice with a little submarine on it to go scooting around in what may be a subsurface ocean. Saturn's moons, very interesting. The Cassini probe has been looking at these moons and sending back amazing pictures. Enceladus here has ice geysers exploding on its surface, and this is actually replenishing some of the rings of Saturn. This moonlet is blowing ice particles out of geysers in, and it also has perhaps some sort of a subsurface ocean, or at least a briny slush. No one's really sure whether it's an actual ocean or just some sort of slush. And this is jetting out continuously around Saturn. Also Titan. It's a huge moon of Saturn, and it's really interesting. Titan has a dense methane atmosphere. It's very cold. This image here is actually a radar image of the surface of Titan, and it shows a lake of methane and a shoreline. The bedrock of Titan would be solid water ice because it's so cold. But it has, similar to our water cycle here on Earth, it would have a methane cycle. So it would have rivers of liquid methane. Be interesting to see what sort of life might be able to exist in such an environment. I've shown this in a previous talk on the Kepler mission. This is a space telescope which is looking at 156,000 stars, and it's waiting to see a planet move in front of the star and watch the star's light dim by a small percentage. And by measuring the percentage of light dimming, it can measure the size of the planet. So out of the 156,000 stars that this observed, this is about 4 months of data. This shows you the size of the stars around which planets have been discovered. Now, to actually discover planets, they have to be orbiting pretty well edge on to us. So there's a good chance that if they're at a high inclination, you wouldn't see them. But this shows you the size of the stars that have had planets discovered alongside with the size of the planets that have been discovered. This is a picture of Earth in front of our sun for reference. So, of the findings, they found 1,235 planets at the time of this publication. 68 of them are approximately Earth-sized. 288 are super-Earth, 662 are Neptune-sized, 165 are the size of Jupiter, and 19 are larger than Jupiter. So, less than 10% of them are actually Earth-sized. And of the 54 of these candidates found in the habitable zone where water might be liquid around their star, 5 of those are near Earth-sized. So this mission is really the first real statistical data we have on one of those numbers in the Drake equation. But it may lead to more data, because now that we see these planets orbiting in front of these stars, we can build a big telescope and look at them, and we can actually watch light passing through their atmospheres. And what we can do is we can take a spectrum of that light, and we can tell whether there's oxygen in the atmospheres of those planets. And what that will tell us, we think, is that whether or not there's actual photosynthesizing life on those planets, creating oxygen. Because free oxygen would normally just break down in the ultraviolet flux of the star, unless it's continually revived by some sort of living or pseudo-living process. But our galaxy contains hundreds of billions of stars. So there's a good chance that there's going to be several of these things. And we saw that life arise relatively quickly after the Earth was formed. So there's a good chance that many of these will have some form of life. But the odds that one of them will have life that we can talk to is relatively small. One other thing I just want to touch on, and some of you may have heard of, it's called panspermia. And this is the possibility of basically planets infecting other planets. So if you have life on one planet, the planet sneezes, and it gets all over another planet. Well, it doesn't actually sneeze. This is the sort of thing that happens. Chunks fly off. We've got Martian meteorites that have been discovered on Earth, and people think that there's microfossils in these. Other people think that it's just non-biological processes and artifacts. There's also been some look in the Murchison meteorite. On the left, we have images of living cyanobacteria, and on the right, we have organic residues found in the Murchison meteorite. Of course, the Murchison meteorite's been sitting in a museum for 150 years, so maybe it's not surprising that it's got mold growing on it. Anyways, also, we know, as I said before, that we have very hardy microorganisms that might survive the trip between planets. This is Deinococcus radiodurans, and it's been found actually in nuclear reactors. It survives radiation levels 1,000 times higher than what would kill a human. And it would actually survive short interplanetary journeys on a meteorite. We know that DNA has a half-life of about 1 million years in fossilized material, or in buried material. And the oldest viable cells have actually been isolated from permafrost that are about 2 to 3 million years old. So it's not out of the question that you could have exchange of biological material between, say, the terrestrial planets. The question then becomes, could you have exchange between solar systems, for example? Well, that's relatively unlikely, because the interactions don't happen very often, and they don't come very close. Say once every 20 million years or so, a star system comes through our Oort cloud, and they might have some type of interaction. So it's not out of the question, but it's probably unlikely. So this is my last slide, and this talks to the possibility of actually detecting other civilizations if they're out there and if they're broadcasting. This is the Arecibo radar dish, which is a great big radio telescope. We've actually only been broadcasting signals out into the galaxy since the start of the radio era and television. We've been broadcasting UHF signals for less than a century, really, at any sort of power. And so you can think of our galaxy as a 100,000 light-year wide disk, and we've lit up maybe 100 light years of that 100,000 light years. So it's a relatively small fraction of the galaxy that could actually detect our communicating civilization, if anyone was out there listening. The other thing to think about, this is actually the only graph in my presentation here. We're showing, this is actually signal versus distance or number of solar systems that the signal might get to. And this represents the leakage from our TV and UHF broadcasts. You can see that at a certain energy, at a certain sensitivity, if we were to say 10 light years away, we would have to have this sensitivity to actually detect our civilization. Well, scientists have actually done a little bit of looking for radio signals in the SETI program, for example. And this is the sensitivity level of a 4-year study on a 26-meter telescope. All sky. They've surveyed the entire sky with a 26-meter telescope over 4 years, and this is what they would detect. So they would not detect our civilization if it was 1 light year away. And we know that the nearest star is 4 light years away. This is a targeted search that was done called Phoenix that observed 800 nearby stars over available channels between 1200 and 3000 megahertz. It would not detect our civilization. So we haven't actually been listening for anyone. We wouldn't be able to detect our civilization if it was at the closest star system. This was the Arecibo radar broadcast that was sent out to the Hercules galaxy. That represents the power of that one message that was sent out back in 1976, I believe. So we sent out a message for a couple days in 1976 at this energy. And so we would have detected it on our all-sky survey if it was within about 20 light years. But this was only one message that we've sent out as our civilization in the entire history of our globe. So what are the odds that someone was listening when we sent that out? So the evidence indicates that we really haven't been talking or listening. So why should we expect to hear or see anyone? There could, for example, be a pan-galactic civilization, and we've made some horrible galactic faux pas, and they just don't want to talk to us. And we must ask ourselves, if they were out there, do we want to notify them of our presence? In such a situation, would we be the Europeans or the Native Americans? Interesting things to think about anyways. Thank you.
Thank you, Al. Al?
Yes?
I want to ask you a question. How do they know, with this dimming, this of the light of the star, how do they know that that star is not an R, Lyrae, or some type of a variable, rather than having a planet?
That's a very good question. The Kepler survey there are a lot of variable stars that they have detected, and a lot of very strange variable stars that pulse in brightness. Most of these discoveries, they've seen them multiple times. So they actually see the signal in a period before they confirm it, like 2 or 3 times. And there are various things that they can check in terms of how, it dims at a certain rate and then bottoms out and then comes back on at a certain rate, whereas pulsations have different shapes to them. So those are the sort of things. There's some that they're not sure of.
Yes, now, you've given us a very good theoretical, speculative discussion based on the Darwinian theory of evolution. And you know me, we've had a discussion on this before. And there are many of us, in fact, the Gallup poll recently in the United States showed that half the population of the United States does not believe in the theory of evolution. Now, it would be good for some of us to have a chance to get up there and show the evidence that there is no Darwinian life anywhere in the universe.
You have a question?
Has to have been designed.
No controversy.
I did not speak about the Darwinian theory of evolution. All I spoke about was the evidence. We can discuss theories to describe the evidence, but what I presented was the evidence.
Well, there's more to it.
Really?
Yes.
Darwin has nothing to do with star evolution.
Well, I'd be glad to give a little.
Show us the
speech on that,
evidence.
too, with the evidence of divine creation in the universe, intelligent design.
I'm out of here.
See you later.
Anyway, someone think about it.
Okay, well, thank you, and I think before we get any further into that, we'll carry on with Sanjeev's talk on the topic of astrophotography as an art form. Thank you, Al.
Okay, so I think I have 15 minutes, right? I'll try to be briefer than that. So I want to talk about astrophotography as an art form. So I'm not up here talking to you as a scientist. I'm going to talk to you more as an artist. And so if there's anything you don't agree with, that's all right, because you're welcome to have your own opinion of art. So now the first thing I want to say is that I'm only talking about one thing today, and that is what I think is the first and most important ingredient in practicing astrophotography as an art form. And again, you're welcome to disagree with me. And I think that is the presence of a conscious mind. Now, what does that mean? I think it basically means you have to suffer. So the more you suffer, to make your images, the more likely it will be seen as art. Now, this is not a sufficient condition, but it is a necessary condition. Okay. Now, I want to start with a short story. Okay? And this is a story from my childhood. And it's a story about a peacock and a mouse. It's a peacock, mouse. Now, I didn't make these images. This is from the web. I can see the image credits up there. Now, this story comes from Hindu mythology. And for those of you who are familiar with Greek mythology, you might know about the Greek gods such as Zeus and Apollo. Well, Hindu mythology has many deities and plenty of stories about their lives. Now, I have to emphasize these are mythologies, so they're metaphorical. Please don't take them literally. Now, this particular story is about the family life of two of these deities, Shiva and his wife Parvati. And one day, Shiva and Parvati are hanging out with their two sons. And these are all gods, by the way. And the two sons are Ganesh, the older one, and Murugan, the younger one. And when an uncle shows up. Now, the uncle is known as a troublemaker, and he's someone who likes to stir the pot. So the uncle has come for a visit bearing a gift, and the gift is a very gorgeous ripe mango. And the uncle says, which of you boys wants this fruit? And of course, both boys want it. And he says, well, there's only one mango, so we have to have a competition and to see who gets the fruit. So we're going to have a race. Now, the mango goes to the one who can go around the world and come back to this spot right here, the fastest, or the first person to come back. Now, if you know anything about Hindu mythology, you'll know that each deity is associated with an animal companion, and Murugan is associated with a peacock, hence the peacock. So he says, no problem. He jumps on his peacock and he flies away at super duper speed. He knows he's going to be back within a few hours. Now, what about Ganesh, the older one? Who is his animal companion? Well, it's the mouse. So he knows that he can't exactly jump on his mouse and go around the earth. So he takes a little break, thinks about it, and what he does is he closes his eyes. He asks his parents to stand next to each other. He closes his eyes and he walks around his parents in meditation. And once he completes that circle, which doesn't take very long, he opens his eyes and looks at his mom and dad and he says, my parents are my world, right? So, my parents are my world. Of course, the heavens open, the angels sing, and he gets the fruit. And his brother Murugan comes back a few hours later after having circled the earth, and he jumps off his flashy peacock, only to find his older brother has already eaten the mango and is now having a nap. So that's the story. Now, you can imagine why the story is a popular one for parents to tell their children, especially in Sri Lanka, where I grew up, because it is a story about filial piety, about devotion to one's parents. But I tell it to you today for a different reason, and that is to demonstrate that the solution we design for any problem depends almost entirely on how we conceptualize the problem. What exactly is the problem? Why is it a problem? And what are we trying to achieve? Now, in astronomy, I think we're obsessed with one thing: signal, right? That's because everything we try to observe is so faint. And whether you're a visual observer or a photographer, there is very little light to work with at night. And this is why we value aperture so much. So in general, a bigger scope equals more light gathering power, which equals more signal. But a bigger scope has to be supported by a big amount. And the bigger we get, the more gadgets that we need to support and control everything. So eventually there's so much gear that one has to build an observatory to house all of it. And it becomes very difficult to carry one's gear to a place of one's choosing and to set up and take down the equipment for each session. So there is indeed a price to be paid for getting this signal. So the question really is, for me, is how much signal do we really need? And I think that question can only be answered if we understand what our purpose is, which goes back to the story. What is it that we're trying to do? What is the problem we're trying to solve? So I want to show you a couple of images just to show, in terms of imaging, how much signal that I think we need. Now this image, I'm going to show you 3 of them very quickly. And this one is 4.5 hours of exposures. And for this image, it's M106, and that's the NGC 4217 in the corner there. I was at Algonquin Provincial Park one night in April this year, and I was set up next to a lake, and I did my RGB exposures, and then the fog rolled in, and my night was done. And then I had to wait another few weeks, and in June I was able to go to a dark sky side neon prior, and that's where I captured my luminance. Now this one, I had used 10-minute subs, and so this image is tracked and it's auto-guided. This is my 5.5-inch refractor. So when you're trying to get more faint detail, well, you need these longer exposure times. This one is only 72 minutes, but this actually is a 3-panel mosaic. Now the first image is only 1 degree of sky. This one is actually showing you about 18 degrees up and down the sky, and I shot it with a 135mm lens. And I didn't have to guide this to the 4-minute sub-exposures. Now, to my mind, there's as much signal here as I would possibly want as in the previous image, but the exposure times are very different. So again, I think it goes back to purpose. What are we trying to do with these things? Now, the larger field of view, I think, is great for showing some of these dark nebulae. This is the Sagittarius region. You might recognize the Lagoon Nebula on the bottom, and up there we can see M17, the Swan, and M16, the Eagle Nebula, near the top corner. And in the middle, the bright patch is the M24. It's a star cloud. Some of you might be familiar with this. These are dark nebulae. You can observe these with binoculars. If I remember correctly, those are, I think, B92 and 93. So this is with 72 minutes, but again, it's a 3-panel mosaic. Now here's one which is only 60 seconds. Now this image is neither tracked nor guided. This is just with a camera tripod and unmodified DSLR. And for this shot, I did on August 3rd this year, and I was standing on some rocks that jut into Lake Superior, and that is about an 11-hour drive from Ottawa. It's a place called Catherine's Cove, and so the 60 seconds. So again, in my mind, there really is no qualitative difference in the level of signal that I'm getting in terms of what I wanted to get in any of these 3 images. But going back to this issue of purpose, I think that if our purpose is scientific, then being able to achieve high resolution or show more detail becomes very important. But personally, I would not describe most of the astrophotography I see on the internet as having a scientific purpose. To my mind, most of these images have one purpose, and that is to show beauty. In other words, the purpose is artistic rather than scientific, or at least a mix of both, right? So if the purpose is artistic, then I think it's relevant to ask where the art is coming from. Does the art come from the sky? Does it come from the telescope? Does it come from the sensor in the camera? And I think to answer the question, we might also want to ask, well, where does music come from, by analogy? Does music come from the strings that vibrate on a violin, or does it come from the heart of the musician? Now, I'm not going to answer that question, but you can think about it. But I think that something very tragic has happened in the way that we practice astrophotography. And I'll qualify it as my own opinion. But I think that in our quest for signal and for increasing levels of precision, we've gone very far down the path of automation. And we've taken many steps to take the photographer out of the picture. In fact, the goal of many so-called dream astrophotography setups seems to be to eliminate the photographer altogether, so that image acquisition is completely automated. For me, that is the opposite of what is required. Wherever I can exercise personal skill or judgment, I prefer to do it myself, rather than have a machine do it for me. And one example I can give of this is the use of GoTo in imaging. Every time we use go-to to point our telescope, I think we're giving up our ability to point the camera. And pointing the camera is half the fun in photography. I don't know of any daytime photographer who allows his camera to be pointed by a machine. Pointing the camera is all about composition. When we surrender our power to point the camera, I believe we give up the personal discretion and judgment that goes into composing an image. I point my camera by first looking up at the night sky, the full sky from horizon to horizon, and then I look at a star chart and I decide what I'm going to do that night. Now, in general, I try to minimize the use of gadgets. I'm suspicious of anything that comes with a cable or requires power to operate in the field. I want to know, do I really need this, or will it just get in my way? I rotate my cameras manually, and I turn the focus wheels on all my telescopes and lenses manually. I try to use my own eyes and my hands wherever possible. I think investing in personal skill is the way to achieve beautiful images. This is not an argument against big scopes. In fact, what I'm now after is the biggest scope that I can carry and safely point on my own. Note also that I'm not talking about scientific imaging here. For a scientist, removing the human variable might actually be quite desirable, so that the results can be repeated consistently. By contrast, in the art world, it is not repeatability, but rather uniqueness, the unique perspective that each human being brings, that is valued. So, with that, let me show you a couple more pictures. Now, this is a sketch of the Virgo galaxy cluster that I did 4 years ago. And it's a sketch I did of the eyepiece through my Daub, my 14.5-inch Daub. And some of you might recognize this picture because this is a photograph of that sketch. It's numbered number 2 down there because it's actually one of 4 sketches I did in May of 2007. We actually had about 7 clear nights that month, and I managed to get out for every one of them. This is near Onpry. I did this sketch. It took about 2 hours. The moon was rising that night at about 12:30 a.m. You can see from my notes. So I did this before the moon came up. And it's inverted. It's actually the M8486 and M88. It's a Markarian's chain. It's inverted because the view through the eyepiece was inverted. The reason I'm showing this to you is, well, there's 2 reasons why I'm showing this to you today. One is that I think a visual observer's approach to his or her equipment is still, for me, the ideal that I try to achieve with my imaging. That is to say, I think the most important thing is not the equipment. It is the relationship between the observer and the sky. The equipment is simply a tool that should get out of the way. As I said at the outset, for me, being present and being mindful are the first and most important ingredients in imaging. Now, the second reason I'm showing this to you is that when we sketch, we actually draw in the negative. So you can see that the galaxies that I would have seen as bright in the eyepiece, I've sketched them as dark. And the background sky, which was dark, I'm representing with the white paper. So we actually sketch in the negative. Now here's another negative. This is a photographic negative, because this is actually my image of M42. And what I've done is just taken the luminance and inverted it. So you can see the trapezium, right? And all the stars are black. And that's a composite, by the way. There's 96 minutes of exposures here, but that includes a lot of 5-second exposures and 30-second exposures, along with 6-minute exposures. And this is something that I did at FLO in November of last year. And this by the way, is a 48-inch print in my show. It's on aluminum. And the other mosaic I showed you is a 40-inch print. So these pictures don't really show you the resolution that you can see if you go to the show and see these in person. So with that, I'll just do a little plug for my show. This image that you see on the show card is kind of like this one, except I've actually brought in the color from the full RGB image, and I've composited it. And I'm calling these inverse composites, because basically I'm showing part of the image in full color and part of it as an inverted image. Now, the show is on for 2 weeks, and it's from October 25th to November 6th, so you can drop by any time at the gallery. It's open to the public. But the best time to come would probably be for the vernissage, which is on a Sunday afternoon, and I'll be at the gallery at that time. So I do hope you get a chance to check it out. I'm showing 26 pieces at the show, and they're all prints on aluminum. So thanks for listening.
Thank you, Sanjeev. Well, worth running a little late? I'd say so. Anyway, just a few messages to finish off the meeting for tonight. I think to start with, I had someone named Anna with a sort of Russian-sounding, unpronounceable last name came up and told me that there's a series of astronomy lectures available off the Yale University website. So for those who are interested in that sort of thing, I know I find a lot of them through iTunes, their university offerings there, but as well, you can check out Yale University and see if there's something you're looking for there. Stanwatt Library, I believe, will be open this evening after the meeting is done. Estelle's pick of the month for this month is The State of the Universe, a primer in modern cosmology, as you can see. Drop by, see her, and pick up a copy or a copy of something else on your way out of the building. Next, please. The Kingston Center is having their 50th anniversary dinner on the, Saturday, October the 22nd, so upcoming. Information's all there. Our members are welcome to attend if they please. We won't leave the slide up long enough for you to write all this information down, but if you are interested, please drop by and ask Chris, and you can transcribe it off the screen before we pack up tonight. But any of the members who wish to go are welcome. Next up, brain kind of locked up here for a moment. Let me see. Paul Cloninger is running another astroimaging course. If you're interested, 2-day workshop, you can get hold of the www.spao.ca. Phone numbers there. Again, if you're interested, come up, see Chris, get the information, write it down afterward. I'm sure there's still space in there, but it sounds like a pretty good program. Post-meeting, as usual, the library, I believe, will be open this evening. Somebody yell out if they know otherwise. Okay. Pardon me? Yes, I saw her earlier. I'm just not sure whether the door's unlocked. Equipment library, you can see Al Scott about that. And if Al is still here, I hope he is, what is it? Don't run away. I've got a telescope in the back of my car that I need to give you. So, gotcha. Let me see. Coffee, conversation, other refreshments out front. Art and Ann Fraser are providing them as usual. If you need to speak to someone, pick up a card, see Art Fraser. He'll be out there. Let me see. Stephen McIntyre, is he here tonight? I haven't seen him tonight.
The library is open.
Oh, okay. I just had whispered the library is open. As far as the magazine renewals go, a special rate for our RASC members, but if you're going to apply for that, has to go through Stephen McIntyre in order for you to get the discount rate on the magazines. But if you're interested in a subscription, you can check with him. Please remember the rest of the museum is open. We're not free to wander off into the rest of the building. Yeah, sorry. Mouth not working. Brain says one thing, my lips say something else. Okay, the rest of the museum is closed. Stay in the lobby. Okay. Anyone else? Anyone wishes to join the group? I never seem to get there, but they're getting together at Kelsey's as usual. So if you feel like joining the group for some chat, head on over to Kelsey's. Good. 119 of you in the audience tonight. Hard to believe, right? Pretty good. Thanks to all the organizers and speakers, except for that first guy. I don't know why they put him on the list. Thanks to our host, Canadian Science and Technology Museum. Without them, we wouldn't have this lovely venue. If you have any suggestions, complaints, other things about the meeting, then my email address is at the bottom there, bill.meeting.chair@gmail.com. Other than that, our next meeting, November the 4th. How many of you noticed that the meeting tonight is actually not when it was supposed to be? Did anybody? Yeah, we planned not to have them conflict with long weekends, and then we ended up with one conflicting anyway. But this was supposed to be next week, but anyway, it got messed up. The next one, though, is on the first Friday of the month. So see you then. Have a safe drive home. Be there, be square. All right.